Hello, this is the lecture for section 6.1, sinusoidal graphs. All right, let's start with a couple definitions. Let's start with the definition of a periodic function. Here's a nice mathematical definition. It says a periodic function is a function for which a specific horizontal shift, call it p, it results in the original function. So in other words, we could say f of x plus p equals f of x for all values of x, right? So all this means is if you shift the function right by a certain amount or left by a certain amount, you get back to the same exact function, right? Then a period is the smallest horizontal shift such that we do get to the same function again, right? So for example, let's look at a visual of that. Let's see. Let's do, this is basically a sine function. You know, if I could do it right, let's make it a little more accurate. Okay, there's a sine function. The period, and it keeps on going. So this is like one period of what the sine function, but it can keep on going after that indefinitely to the right or to the left. Drawing so good freehand. But it repeats itself after this one period. See the same graph again? And then it would keep going, same graph again. Right, so we would say that this is the period of the function part, the smallest portion that doesn't repeat itself. All right. So all trig functions are periodic in nature, and we refer to them as sinusoidal functions. All right, we're predominantly going to look at the sine function and the cosine function here, but there is a function for the tangent, a graph, I should say, for the tangent, as well as the secant, cosecant, and cotangent. We won't focus as much on that as we will on the sine and the cosine. All right, so let's investigate these periodic functions, the sine and the cosine, a little bit further. I don't think my tablet's going to let me do that. So let me do a drag here. See if I can get it Desmos. There we go. All right, so what we're looking at here is a unit circle that has been drawn on the origin. And, well, we're going to stretch our graphing definitions just a little bit here. But what we're looking at on the horizontal axis is going to be the angle measure for the unit circle, right? So 0, pi over 2, pi, 3 pi over 2 pi. So here's 4/4 of once around the unit circle, right? And then the y-axis is just our numbers, 1, 2, 2, 3, 4, and then -1, -2, 3, -4. All right, so we have a unit circle here. The largest value of y would be 1. The smallest value of y is -1. All right, so if we were to graph the sine function here, let me start this slider so we can see what's happening. Okay, if we were to graph the sine function, the x-coordinate of any point on that graph is going to be the angle measure, this right here, okay? And the y-coordinate is going to be the y-coordinate of the terminal point, right? Like we see here as it goes around, the y-coordinates of all those points. Let's see if I can get to show them. There they are. Well, it's going fast, isn't it? It's making me crazy. Let's stop it. All right, so that's where we're getting the data from. Now let's take a look at what the sine graph looks like. Let's put it on there. It's in green. All right, so here we've got from 0 to pi over 2. I'll move it over. This little green. This is the first quarter of one period of the sine function, right? So as the angle measure goes from 0 to pi over 2, y goes from 0 to 1. Look at your unit circle there. At pi over 2, the x-coordinate is 0, the y-coordinate is 1. Okay? So here's what our sine graph is going to look like. Let me start that slider so we can see the rest of the graph. Right? As that angle gets larger, We can see that the y values fluctuate in between +1 and -1. We see that it's a periodic graph. It's just repeating itself every 2 pi. Okay, now it could go to the left as well. I just don't have this particular animation set up to do that. Now let me stop that for a minute. Let's put that sine away and let's look at the cosine for a minute. Okay, the purple graph on here is the graph of the cosine, all right? On this graph, the x-coordinate is still the angle, and the y-coordinate is actually going to be the cosine of that angle. And recall that the cosine of an angle is the x-coordinate of the terminal point on the unit circle. Okay? Yeah, think about that for a minute, right? Let me start that animation again, and we can see what the cosine graph looks like. You can see it's periodic in nature as well. It repeats itself also every 2 pi, because 2 pi, of course, is once around the unit circle. All right, so here we've got, let's see if I can get it right, showing one, oops. Let me see if I can just have it show one angle, or one, I'm sorry, one period. There we go. There's one period of the cosine function. Okay, so the cosine function, without any transformations, it always starts up here at 1. A quarter of the way through the period, it hits the horizontal axis. Halfway through the period, it hits the low point. 3/4 of the way through, it comes back to the horizontal axis, right? And then at the end, all the way around that unit circle, or at the end of the first period, it goes back up here to 1, to its high point. Right? This is a basic shape. This is the shape of a one period of the cosine function. Let's compare that to the sine function. Okay, the green one I just put on there is one period of the sine function. Right? It goes from 0 to 2 pi, of course, once around the unit circle. Again, the x's are the angle measures. The y coordinates of all these points are the sine of that angle measure, which is going to be the y-coordinate of the terminal point on the unit circle. All right, so there's some interesting things to observe here, right? The sine and the cosine functions are very similar, like in a number of ways, but graphically, we can see, if you can visualize this, we can see that the cosine and the sine graphs, they're actually the same, but one is shifted horizontally by pi/2, right? So we could say that the cosine function is shifted either left or right of the sine function by pi/2, or we could say that the sine function is shifted left or right of the cosine function by pi/2. Okay, they both have the same period, 2 pi, without any transformations, right? They oscillate between 1 and -1, the output of those functions. All right, let's go back to our PowerPoint. See if I can get this. This is Desmos, by the way. Get that out of there. All right, so we were just discussing most of these, but let's point this out again. The domain of the sine and cosine, if we don't limit it, it's all real numbers. As we could see from that animation, it'll just keep on going and going. To the right, it can also keep on going indefinitely to the left. All right, the range of the sine and the cosine function is -1 to 1, right? It oscillates between -1 and 1, okay? These graphs are referred to as sinusoidal graphs. Both the sine and the cosine function are referred to as sinusoidal graphs, and they both have a period of 2 pi. In other words, they don't repeat themselves until they hit 2 pi. Okay, and that makes sense, right? Think about your unit circle. Once around the unit circle is 2 pi radians, right? Or in degrees, we could say it's 360 degrees. All right, so given that information, let's take a look at these graphs. And let's talk for a minute about symmetry and whether or not the functions are even or odd. Okay, the first one here, this is a sine graph. All right, here's one period from here to here. It's got that shape. That's something you need to be very familiar with, the basic shape. Call this a toolkit function. The basic shape of the sine function without transformations. It goes up, comes back to the middle, goes down, and stops where it starts. Starts at the middle, ends at the middle. This is the sine of whatever angle measure. We're going to call them t. We've been calling the angle measures t in this section. All right, so there's the graph, the function. Call him f of t. This one down here is the cosine, right? Let's just look at one period of it. Starts high, goes to the middle, goes low, comes back to the middle, ends high. This is your basic shape, or your toolkit shape for the cosine function. Okay? Now, what do you notice about the symmetry of these graphs? If we look at this sine graph up here, is it symmetric over the horizontal axis? If we flip it over, is it the same? No. Is it symmetric to the vertical or y-axis? So if we flip it across y, is it the same? No. Is it symmetric to the origin, though? Right? So if we think about this as an old-fashioned game spinner and we spin this around 100 degrees, will we end up with the same graph? Yes. This one is symmetric to the origin. Okay, and look at the symmetry of this cosine graph here. Not symmetric to the horizontal. This one, not symmetric to the horizontal. Spin that around 180 degrees. It's not the same. But the cosine is symmetric to the vertical or the y-axis. Since it's symmetric, so this one is symmetric to the vertical axis. Okay, think back for a minute earlier in the course. Symmetry to the vertical axis or the y-axis means that this is an even function, right? Since it's symmetric to the vertical axis, then we say that it's an even function. This one up here, since it's symmetric to the origin, the sine function, we then say that that is an odd function, all right? And recall that for odd functions, f of negative x would equal negative f of x, right? And recall that for even functions, right over here, f of negative x would equal f of x. Same thing, change all the x's to negative and get the same, and simplify, and you end up with the same function. So because of the nature of the sine function and the cosine function, we have the negative angle identities that state the sine of negative theta is equal to negative the sine of theta, right? And again, that's just the definition of an odd function, right? That's why we have that identity. And then we also have that the cosine of negative theta is equal to the cosine of theta, and that's just the definition of an even function, all right? So these identities are on your formula sheet already. I just thought it was kind of interesting. There isn't really even a proof for those. If we just look at them for what they are, we can see why those identities are true. All right, so let's move on and talk a little bit about transformations of the sine and the cosine function. We've got all those transformations. Remember, we can shift a function or shift a graph up or down, left or right. We can stretch or compress a graph vertically or horizontally. We can also reflect it, right? We can reflect vertically or horizontally. Well, let's see. Take a look at the sine function. If we stretch it by a factor of 2, all right? So one thing we have to be really familiar with is the non-transformed shape of the sine, right? And oops, the non-transformed shape of the sine, it's really easy to draw. We know that the period is 2 pi, so it starts here, ends at 2 pi, okay? We know it comes up, hits the middle, and goes down again. Here's our middle. It'll oscillate between 1 and -1. Okay, so if it goes up, comes back to the middle, it hits the high point, a quarter or pi over 2 ways through, or which is a quarter of the period. When it comes back to the middle, then it goes down to -1, and then it comes back to the middle. Okay, there's one period of the sine function. Of course, it does keep going. You know, I could do it over this way too if I wanted to have some more. There's 2 periods now. If I stretch that, right, if I stretch that by a factor of 2, all these y coordinates get multiplied by 2, right? So let's put 2 times the sine theta over here. Compare them. This guy is the sine of theta. All right, 2 times the sine of theta. So we're multiplying all the y's, or all the outputs of the function, which is the y's, multiplying by 2. Well, 0 times 2 is 0. Over here at pi over 2, y is 1, right? Well, 1 times 2 is 2. Let's see, there's 1, there's 2. So it's going to go way up here now. 0 times 2 again is just 0, so it's going to come right back down here. All right, so far we have this much. -1 times 2 is -2, so it'll come down here, and then it'll come back here. All right, so there's 2 times the sine of theta. Should round that out a little bit more. I'm not good at freehand drawing on this tablet. So there's one period, and, you know, I mean, I could continue it too. What's -2? Let's put that in. -2 is down here. If I wanted to continue it, it would look like this. There's 2 periods. Okay. Now, it's important to note there's some terminology that's a little different with sinusoidal graphs than other graphs in the Cartesian plane. We call the middle, the vertical middle of the graph, we call that the midline, right? And then that distance between the midline, so let me put it in here. This would be the midline, and this midline is the y-axis. I'm sorry, the x-axis. So it's the equation y equals 0. All right. Then the distance between this midline and high point, or the midline and the low point, is referred to as the amplitude. Right. So for this function here, so that's that distance. It could be here or here. It's a distance, so we don't care about positive or negative, right? So for this function, we would say that the amplitude is 2, right? So instead of saying all this is saying is we vertically stretch the graph by 2, but when we're referring to sinusoidal functions, we call that the amplitude of the graph. Okay. All right. So the center value I just mentioned is called the midline of the function. This midline corresponds to a vertical shift. All right, go back here and think, what would happen if I had a vertical shift? Say I wanted to graph 2 sine of theta plus 1, right? That's how, if this was a function, f of theta is equal to 2 sine of theta plus 1. So what would this mean I would do? I would take this function here, which was 2 sine theta, and I would just move the whole thing up 1 unit, right? So this 2 sine theta plus 1 would move the whole thing up 1 unit. Let's see if I can do that real quick. Something like this, right? All up 1 unit. Well, what happens to that midline? I'm not drawing it the best, but what happens to that midline when I move the whole thing up 1 unit? So on and so forth. Terrible sketcher, folks. Art was never my strong point. There. What happens to the midline? The midline also moves up 1. All right. So the midline of the function corresponds to the vertical shift. It tells us what that vertical shift is going to be. Normally it's 0, because y equals 0 is the midline. But if we moved it up 1, the new midline would be y equal 1. Okay. All right, so look at this graph here. Let's see if we can determine the amplitude, midline, and period of this particular function that's graphed here in red. All right, let's see, where's our axes? They're not hard, they're kind of hard to see. This is the vertical axis right here. Here's the horizontal axis. Okay, so it's easiest to start with the midline. Where's the midline? Well, we can see that it's not the axis anymore. That's not in the middle of the graph. Where's the middle, the exact middle of the graph? So we're looking for halfway in between the low point and the high point, right? The high point is at y equal 8. The low point is at y equal, I drew over it, but it's -2, right? Well, what's halfway between 8 and -2? It's 3, right? So here's the new midline, or the midline for this graph. It's right here at y equal 3. Okay, so midline, y equal 3. Okay, now that we know the midline, it's easier to start there. Then we can find some of the rest of the things. The amplitude is simply the distance from the midline to the high point or the low point, right? That's our amplitude. What's the amplitude? 1, 2, 3, 4, 5. So we'd say the amplitude equals 5, right? And then what else? The period. All right, so the period, this is the smallest interval for which the graph doesn't repeat itself, okay? So I want to think about a sine or a cosine, doesn't matter which, right? Because the sine and the cosine are just horizontal shifts of each other. Well, I like to start at the vertical axis when I can, and if I were to start the vertical axis, I can see that this might be easier to define as a sine function, going from here up to here, back to here, down to here, and ending right there. That would be one period. All right, so how far is that? It's not saying it on here, but I think it's going to be 2. I'm going to say that that point right there, not this one, oops, that point right there, I'm going to say that that point right there on the horizontal axis is at 2 pi over 3. If it was labeled, let's pretend it was labeled 2 pi over 3, okay? So that means that's going to be the period of this function. That's the smallest interval for which it doesn't repeat itself. Right after 2 pi over 3, look, it's going up again. It's starting to repeat itself. Okay, right before 0, it's going down. It's repeating itself. So our period then is going to be 2 pi over 3. Not too hard to determine those from visual inspection on the graph. All right, so you know there's other transformations that can occur. We've talked about a vertical compression or stretch, okay? And we've defined the period. We've talked about a vertical shift. We can also have a horizontal compression or stretch, right? So if we look at a, if we look at a standard form for the sine and the cosine function, we could say it would be a times sine of bt plus k, or cosine bt plus k, where b is our horizontal stretch or compression. Well, same as with other functions, right? Think back on your transformations. Okay, so in the standard form here, A, of course, this is our vertical stretch, or we call it amplitude with sinusoidal functions. K is our horizontal shift, right? But we call it midline with sinusoidal functions. Okay, same thing with the cosine. Now, B is a funny thing. It is our horizontal stretch or compression. It's related to the period, right? But what it is the period is equal to 2 pi over b. So if we arrange this, then we can always, if we know the period, we can always find b, because b then is equal to 2 pi divided by the period. All right, so when we have a standard period, when there's no horizontal stretch or compression, right? The period is 2 pi, so b is 1. Okay, so there's no coefficient in front of the input variable, or t. In this case, we're using t. Okay, does that make sense? Okay. All right, so given this information, let's look at an example here, and let's see if we can determine the midline amplitude and period of this function that's given here. F of t equals -4 times the cosine of 4t minus 1. All right, let's start with the midline. It's a nice one to start with. The midline here relates to what we're adding or subtracting out at the end, right? We have our standard form, it's the k. So the midline here is going to be, let's say equal, let me do it like this. The midline is going to be y equals -1. The line y equals -1. All right, the amplitude is never hard. It's the absolute value of the coefficient out here, right? So the amplitude on this particular function is going to be 4. Now, amplitude is just measuring the distance. It's just the stretch. It doesn't matter about the negative. It doesn't change the amplitude at all. But what does that negative indicate? It indicates a vertical reflection. So I might write that down just as a note. Reflect vertically. All right, but we do still need to find one more thing, the period. Okay, so recall that the period is 2 pi over whatever this b is going to be, isn't it? So in this case, our period is going to be 2 pi over what is b? It's 4. 2 pi over 4, and that'll reduce down to pi over 2. Okay? All right, let's look at another example. Here's a graph. We'll see if we can write the equation or find the formula for this sinusoidal function that's graphed here. All right, well, let's start. Here's our vertical axis. Let's start at the vertical. All right, and the first thing we want to do is we want to decide if we're dealing with a sine or a cosine. All right, so let's start at the vertical and find one period. So this goes down, not down. Looks like this is where period ends. Okay, what shape does that most resemble? Is it the sine or the cosine? Remember that the sine function, and let's put our standard forms up here. Let me just write those down. We can have the a times the sine of b t plus k, or a times the cosine of b t plus k. Okay, now your shape, your general shape for the sine function, remember, is it starts in the middle, goes up, comes down, ends in the middle. Your basic shape for the cosine function is starts high, comes to the middle, goes down, middle, and then high again. All right, this is one period of, maybe call it a toolkit function, right? A non-transformed. It's your basic shape. Well, what basic shape does this resemble? Clearly the sine function, except, look, it's a reflected, isn't it? All right, but it's a sine. It's definitely a sine function. It's not. It doesn't do what the cosine function is. So I've decided I'm going to write the equation for a sine function here. Now later on, when we talk about horizontal shifts, we could have chosen a cosine function, but I haven't shown you how to do that yet. Because look, from here to here, maybe you can see a cosine, right? Or from here to here, you may see a reflected cosine. So we're just going to go with the sine. Where's the midline? Halfway. So the midline is going to be right here. My pen will work. There we go. There's the midline, and that's at y equals -2. Okay, so I can write some of this, not all of it, but I know I have the midline at -2, so I can do this plus k, except it's going to be minus since it's negative. I can stick that -2 out there. We're going to call our function f, and we're going to use t as the input. All right, what next? I can find the amplitude. What's the amplitude? There's our amplitude, okay. What is that distance? 1, 2, it's 2 units, okay. So our amplitude is 2, and this we just, it was a reflection, wasn't it? Normally it would have gone up, back to the middle, then down, but it didn't do that. It went down to the middle, then up, so that means it was horizontally reflected over the midline. right? So I need to stick a negative in front of there. I got this too crunched in. I'm going to make it spread it out more. -2 times the sine of. Now, we need to find out what b is. So our input variable is t. What is b? And by definition, b, right, is 2 pi over the period. So what's that period? Goes from here to here. Starts at 0, ends at 4. So it looks like the period is 4. Right? See that? That's the distance that it takes to repeat itself. So the period is 4. So that means b is going to be 2 pi over 4. Or it's the pi over 2 when it reduces down. Okay, so pi over 2 goes in the slot for b in the pattern. And there's the equation for this sinusoidal function that's graphed here. All right, let's take a look at an application. Say there's a Ferris wheel, okay, a local fair. Anybody go to the Cumming State Fair or the Cumming Fair? It's not State, but the Cumming Fair. My daughter went last week. Anyway, the application here involves a Ferris wheel. It has a diameter of about 85 feet, and it takes 6 minutes to complete a full rotation. All right, passengers board from a platform that's 5 feet above the ground. Write an equation for a rider's height above the ground over time. All right, well, let's see. Let's draw a little diagram. So here's the Ferris wheel. So it had a diameter of 85 feet. All right, so there's the diameter, 85 feet. And it's got this little platform that's 7 feet above the ground. So that's 7 feet, and then here's the ground. Okay, rough diagram just so we can see what's going on. Okay, so people get on, they go around. They might go around a few times. All right, so we need to write an equation. What do we want our equation to be? For the rider's height above ground over time. All right, so we're writing an equation for height. So I think I'll call my equation h. And it's over time, so the input variable is going to be time. So I think I'll use t as my input variable. All right, so I'm going to write the function h of t. All right, so now I need to decide, is this going to be a sine or a cosine? I know it's a sinusoidal function because this height changes to here, but then it changes the same things back again, and then it just repeats itself again and again and again. Circular motion is always going to be sinusoidal in nature. It might be a sine note or it might be a cosine, right? Well, if we want to find an equation for height with time as its input, let's see. Graphically, what would that look like? Well, let's put a graph here, like a Cartesian plane. There would be the horizontal. It's t for this, not x, but t. And then there's no negative time, so I'll put my vertical over here. And there's no negative height either, so I don't really care about the negatives. And that's going to be height, or h of t, on the vertical. All right, that's my h of t function. Now what's happening? Here's time 0. Oh, and it says it takes 6 minutes to complete a full rotation, right? So it's going to end somewhere. It'll repeat itself again, but we're just going to put one period down. So we'll say it ends after 6 minutes, right? So halfway in between 3 minutes and we 1/2, but I'm not going to label those right now. All right, so what's going on here with this? All right, we start at 7 feet. So there's our 7. So at time 0, we're at 7 feet. Okay, when we get halfway around, that would be at 3 minutes, right? If it's evenly traveling, we'll assume that it is. So after that time period, it's going to be right up here. So it's slowly going up. At 3 minutes, it hits the maximum, and then look, it goes back down again. All right, so for the rest of the time, it's going right back down till you're at the platform height again. Right? So there's what one time around the Ferris wheel looks like if we're graphing height above the ground. What is this maximum height? Let's see. It's 85 plus 7, right? Or 92. So this is what I always do. I always want to sketch what I think that graph is going to look like. Then I decide if I'm going to write a sine or a cosine. Now this looks to me like a cosine, right? Remember, cosine, it starts high, goes down, goes high again. This looks like a reflected cosine, doesn't it, one period, right? And our standard form for the cosine, was f of t equals a amplitude times the cosine of b t and then plus k. We're going to talk about horizontal shifts too. We just didn't get to that yet. So that's all we're going to be dealing with. This is what cosine looks like. I'm choosing a cosine. This looks like a reflected cosine to me. Remember, sine is this guy. It does this, and it can be reflected too. I'm not seeing that happening in one period here. So I'm going to choose cosine. So h of t is going to be something. I haven't figured out the amplitude yet, but it's going to be the amplitude times the cosine. I'm going to write down what I have decided. I don't know what b is yet. T is my variable, so I can write that much down. How do I go about finding these things? All right, well, let's find the midline of this graph. All right, we'll say it's right here, halfway between the high point and the low point. Well, what's halfway between 92 and 7? It's, well, let's see, 92 minus 7, that's 40, that's halfway in between 92 and 7. Got that from it, 740, it'd be 85, 90, it's 42.5, but I've got to add that 7 to it because it's not at 0. So this is going to be 49.5 on the graph right here. Are y'all with me on that? Let me show you how I did that. The radius here is half of 85, right, which is 42.5. And that's the midpoint on my graph, the midline, sorry, on my graph, right? But on the vertical axis, I got the 42.5, I have to add the 7. So that's how I get the 49.5, all right? So there is my midline. I want to say plus 49.5. What's the amplitude? Now I've got the midline. The amplitude's not bad. It's just this distance here. So 92 minus 49.5 is my calculator. Handy. No, there it is. 92 minus 49.5. 42.5. Oh, well, of course it is. It's the radius. I didn't need to calculate that. It's getting late in the day and I'm tired. All right, so 42.5 is my amplitude. But I'm reflected, right? This cosine graph is reflected, so it needs to be negative, okay, to indicate I've got a vertical reflection going on. Now I just need b, all right? Well, b is 2 pi over the period. What's the period? 6, right? 6 minutes to go all the way around. So b is 2 pi over 6, which reduces down to pi over 3. All right, so pi over 3 completes the equation for the height of somebody riding this Ferris wheel over time. All right, let's see this a little bit more. Let's get to this horizontal shifts. All right, now that we've got, oops, I don't know what just happened. Okay, now that we've got everything else done, let's add this last piece in. It can be a little confusing. The horizontal shift. All right, so we know how transformations work. If we're shifting, we're adding or subtracting to the input variable. But we've got to be careful with sinusoidal functions, right? The standard form that addresses a shift, a horizontal shift, has b factored out. See that? If it wasn't factored out, this would be, I mean, and this is perfectly fine. You do tend to see them this way, but it would look like this. It would be bt minus bh, right, plus k. If we didn't have that horizontal stretch or compression factored out the way it is here, it would have to look like this. right? So you have to be very careful. A lot of times they're presented this way, but in order to find what that horizontal shift is, you've got to factor out any coefficient in front of the variable, all right? And it applies the same to the cosine. So let's look at an example. Here we have this graph, f of t, 2 times the sine of pi over 2t minus pi over 4, and then plus 3. And we want to describe in terms of the original sine. So we want to just describe the transformations that are taking place here. All right. It's very tempting to say that we've got a horizontal shift. Let's see, that's negative. So horizontal shift right of pi over 4. But it would not be correct here. Why is that? Because look, I have a coefficient in front of the t. It hasn't been factored out yet. So the first thing I want to do is rewrite that so that b is factored out. Okay, b is pi over 2. That's easy enough to see. But I need another set of parentheses here, t minus. And what is pi over 4 divided by pi over 2? Remember dividing fractions here. Keep the first, change the multiplication, flip the second. It's going to be pi over 4 times 2 over pi, right? Pi's divide out, 2/4 reduces down to 1/2. Okay, so this is going to be pi over 2 times, in left parenthesis, t minus 1/2. All right, then plus 3. I always want to use it in that factored form. Now I can describe the transformation, right? So what's going on here? We do have the amplitude is 2, right? So I might do this. Since the amplitude, let's spell that wrong. I'll just call it amp, equals 2, right? We have a vertical stretch by 2. Okay. Now what else? Over here we do have a B here, so this is going to be our horizontal. So we'll say since B is pi over 2, we have a horizontal. Is that a stretch or a compression? Let's see. Horizontal. Let me get this right. Horizontal. Sometimes some days writing. Horizontal. Still can't. There. We have a horizontal. Now stretch or shrink. Well, let's see. Pi over 2, that's larger than 1, isn't it? That's larger than 1. So that's going to be a horizontal compression. And that's going to be by pi over 2, right? Okay, so then next, what else is going on over here? We have a horizontal shift, all right? Shift, and look, because it's negative, remember it's counterintuitive on these horizontal shifts. We have a horizontal shift right, not left, but right, 1/2 unit. Okay, and then lastly, there's that plus 3. So we have a vertical shift up 3 units. Okay, and that's the transformations we see going on. All right, so let's end with one more example. Let's see if we can write the equation or find the formula for this sinusoidal function that's graphed here in red. All right, so we want to find a formula. All right, well, I love to start at the vertical axis, but look, at the vertical axis, I do not have the beginning of either a sine or a cosine, right? Remember, and we've got a basic shape we need to be thinking about. Sine, basic shape for the sine is this guy. Basic shape for the cosine is this guy. Neither one. So I need to decide, am I going to do a sine or a cosine? Now I can write both, and we will write both. But which one should we start with? Well, I think that the one I happen to be seeing first is a cosine that's right reflected because I don't want to reflect if I don't have to. I want to keep it simple if I can. So I see a cosine shape here. It matches my cosine shape and it's not reflected. So I think this is the one I'm going to start with. I'm going to see if I can write a cosine. Now let's put our standard form here so we have it to look at. F of t is equal to a times the cosine of b t minus h and then plus k. All right, so next thing I'm going to need before I start writing things, I know I'm going to do a cosine. I've decided a cosine. I might write it just to say, okay, I've decided that, but where's my midline? Okay, well, here's my midline right here at y equals 3. All right, and then I can easily determine the amplitude either here or here. They're the same. Here's my amplitude. And my amplitude I can see goes from 3 to 6, so my amplitude equals 3. So let's see, I can start putting some things in here. I can say f of t is equal to 3. That's my amplitude. So 3 times the cosine. I don't know b yet, but I do know my vertical shift, so I can put that in there. It's y equals 3, so I've got a plus 3 going out on the end. So now I've got to figure out what b is, and h, my horizontal shift. All right, so let's see. Let me just put them in there like this first, and then we'll erase and put the right thing in when we find it. Okay, the horizontal shift is not bad, right? Normally, this cosine curve would start here at the vertical axis. It's moved to the right. How many units? 1 unit. It's moved to the right 1 unit. So that means moving the right is subtracting, right? So this is going to be a minus 1 right there. Now the last thing I need to determine is b, okay? And we remember our formula. To find b, we divide 2 pi by the period. So I need to know the period. What is the period? Well, the period goes from 1 to 9. So it looks to me like the period is 8. All right? So then b is going to be 2 pi divided by 8, or that'll simplify to pi over 4. All right? So I can put b in there, and now I have my equation. All right? So because sine function is a horizontal shift of a cosine function, every cosine function is a horizontal shift of a sine, I can also write this as a sine. Let's see what the sine would look like. Well, where is a sine? Let's find a sine. How about, you always want to include, the vertical axis, because that's going to be the smallest shift, right? So it looks like from here to here is 1 period of the sine function, right? Does it have a different amplitude? No. Does it have a different horizontal compression or stretch? In this case, it's a little bit of a stretch. No, it's the same. So that's going to be, is still going to be pi over 4. The shift is different though, isn't it? Look, we're shifting, instead of shifting right 1, now we're shifting left 1. So it's going to be plus 1 instead of minus 1, right? Because this one we're shifting right. I'm sorry, left. I did it backwards. We're shifting left. Up here we were shifting right. All right, but and then we have the same vertical shift, plus 3. Okay. Now, if I wanted to, I could also write I could pick a portion of this graph and write the equation with a reflection over the midline, right? Look, if I wanted to, I could go from, let's erase some of this, I have too much on here. I want my midline to stay. I could go from, say, here to here and have a reflected cosine with a different shift. Let's see if we want to write that. What would that one be? Well, the amplitude is the same, but now I'm reflecting the cosine. I'm going down, up, instead of up, down, up. So it's going to be negative 3 times the cosine of pi over 4 times t. And I've got a different shift going on too, don't I? I can either shift left 3 or right 5. It'll be the same graph. I think I'll go left 3. So I'll say t plus 3, right? And I still have the same vertical shift, up 3. Okay, there's an infinite number of equations that I could write, right, by picking different portions of the graph with different horizontal shifts and maybe reflections, that when I put them in the graphing calculator, or if I put them in Desmos, they will be the same exact graph. All right, and this ends the lecture for section 6.1.